be doing test 3 wrapper for Physics 2212. And the question that I'll be focusing on is question 4. And the question itself asks that a conducting loop is pulled out of an area with a constant magnetic field, B external, pointing into the page. The loop has a resistance of R, a height of h, and a length of L, and is pulled with a constant force F at an unknown speed. So, the first part of the question, part A, asks us first to indicate the charge buildup on a conducting loop. So in this diagram, as I've already had it labeled, we know that the charge loop is being pulled out this way. And then we can say that the positive charges build up right here, and then the negative charges build up right here. And then the second part of the question asks us to draw and label an arrow representing the net magnetic force on the loop. So we know that net magnetic force can be calculated by Q, V cross B. So we know that since our force is in this direction, we know that the force is going this way, and then as stated earlier, the magnetic field was going down the page. So using our right-hand rule, we can point our fingers in the direction of the velocity or the force as well, and then cross our fingers down into the page because that's the direction of the magnetic field. And then we know that our the net magnetic force is going to be pointing out this way. So as you can see in my diagram, I've labeled the force of the magnetic field going in that direction, which is opposite to the force that we have right here. And then the last part of the question asks us to draw and label an arrow representing the conventional current. So as you can see in this diagram, because the positive forces here, the positive particles are here and the negative particles are down here, we can see this loop as a battery. And so we know that when we have labeled a conventional current in a battery, in a loop with a battery, we know that the conventional current goes out of the positive and ends at the negative. So in this case, it's going out of the positive terminal, and then down this way, and then back into the negative terminal of the battery. Then, the second part of the question, part B, asks us to calculate the magnitude of the current through the conducting loop, and the answer should not depend on the velocity. So as we know, since the loop is being pulled out at a constant force, we know that our F net is going to equal 0. But our F net is going to be the superposition of our force as well as our magnetic force, and they're going to equal 0 together. And then we know, based on this, as I described here, F net is going to equal 0, and it's a superposition of the force plus the magnetic force. And then we can manipulate this equation to say that F plus F mag is going to equal 0, and then that F is going to equal F mag. And we know that the definition of the force of the magnetic field is going to be I times H times B. And we're using H in this example because based on our loop here, we're using we're using this height right here. And so we're going to have I times H times B, and we want to be able to solve for the conventional current. So in order to we need to isolate I. So we know that we can bring this H over B onto this side, and we know that I is F over H times B. And then the last part of our question, which is part C, asks us to determine the loop, the speed of our loop. So we need to basically solve for our velocity. So the way I approach this question, The way I was able to approach this question was that I knew that the force of the magnetic field is going to equal the force of the electric field. And then we can expand these into their definition. So the force of the magnetic field equals Q times V times B, and then the force of the electric field is going to be Q times E. And then we know that the Q's cancel out on each side, so we're left with VB equals the electric field, and then we can manipulate that to isolate our velocity, which is going to equal our electric field over our magnetic field. Now that's not enough. We have to be able to expand our equation even more, or our definitions even more. So we know that the electric field also equals delta V over H, and then all over, so we know that electric field can be expanded to delta V over H. And then we know that delta V can be expanded into I times R. So now what we have is, altogether we have IR over H all over the magnetic field. And in this case we know that I equals F over H over B. So as we continue to manipulate this equation, we can get F over HB times R, so F over HB is our I, and then we have R, and then all over H, and then this entire definition is over the magnetic field. And so as we continue to use algebra, we can finally determine that the velocity equals F times R over H squared times B squared.